Okay, so we're moving on to the next chapter. So, as I told you in this course, we're basically the so-called bioreaction engineering is nothing but kinetics plus transport processes. And I also gave several examples in the first lecture of why, when scale is important, when you're dealing with large scale, then uh, transport processes start to play a role because you have to get things in the right place. Now, this chapter deals with momentum transfer. So, this is about uh, how do you get momentum into the reactor. And by momentum, we mean basically mixing. And why do you want to mix? Well, these reasons are given. Um, we will first be considering we want to disperse the gas, such as air, uh, to the liquid in the form of small bubbles. That is, you could say, goal one. This is what we will be covering. And then the second goal is maintain the cells also fully suspended inside the reactor. This is the second thing that we'll be doing. And the third thing that we'll be doing is to keep the liquid phase itself well mixed. So, let me repeat that. The first idea is to keep the gas fully dispersed in the form of fine bubbles throughout the volume of the reactor. The second one is to make sure that the cells don't settle down at the bottom, that they remain suspended equally in all parts of the reactor. And the third one is to make sure that the liquid itself doesn't have dead volumes, that it is well mixed at every point inside the reactor. That's, of course, the ideal goal. Um, the fourth one, which is actually part of the next chapter, not this one, uh, is well mixed liquids also allow efficient heat transfer. But that we will deal with next in the next chapter. In this chapter, we'll be dealing with 1, 2, and 3 in that order. So before covering it, I think it's important to understand what a reactor is and its dimensions. And I think the book is kind of, my opinion, maybe my attitude towards these things is a little bit different, but a bit too lengthy and too much detail. So I've tried to compress this into to a, to a more concise description of what a reactor is and what its components are. So this is figure 8.1 of Duran, and basically what it shows is that the main components, so the main components of a bioreactor. So at the top is this stirrer motor and gearbox drive unit. This is the unit with a motor inside it that generates the torque. And this torque is then transmitted by the stirrer shaft to the impeller, about which I shall have more to say later. So the stirrer shaft is transmitting the torque, and the impeller actually does the job. The impeller is the thing that is turning inside and agitating the liquid. Now, um, at the bottom of the reactor, you have what is called a sparger, and this is just any kind of a device through which the air enters the reactor. It can be as simple as a pipe with a single hole, or it can be an entire ring with multiple holes on it, a ring of holes, so to speak, that makes some attempt to disperse the air to the into the liquid. And finally, you can see the shaded region consists of baffles. I'll come back to that in a little bit more detail. But let's flesh this diagram out in a little more detail. What you are seeing over here with the motor and the gearbox drive unit on top, right, and the impeller sitting below it. This is actually known as a top drive unit. We also have what are called, this I will show by, so if you see the picture on the right hand side, the right hand side shows you what is called a bottom driven. Uh, this is a bottom driven um, reactor. Notice that the stirrer motor and the gearbox unit are at the bottom, and then from the bottom you have this um, stirrer shaft. It pierces through the bottom, and on top of that sits the impeller. Um, this drive, this type of a bottom drive unit, not typically used because it's mechanically problematic. I mean, this particular portion, this portion can often lead to leaks. You have to make sure that the manufacturing is of really top quality to prevent leaks from happening. But in certain cases, it becomes essential. And our department, in fact, your labs, will be done not with top driven but with bottom driven reactors. These are simply the reactors that were given to us by Switzerland many, many years ago, and they've now been installed in the UG lab. This bottom driven reactor is used for two reasons. One, suppose you want to install many, many probes in the head plate, right? So I'm drawing these vertical lines. So there's a pH probe, there's a DO probe. You may want to have a probe for measuring the biomass concentration. You might want a probe for measuring the redox state in the reactor. Well, if you have so many probes, then the head plate is kind of all used up, or that's where you want to keep your space. And therefore, the stirrer is moved to the bottom to save some space on the top. That's one reason why you want to use um, the the bottom driven system. The second reason why you might want to use the bottom driven system is if you have very viscous cultures, because to turn viscous cultures, you need a lot of stress is faced by the impeller, and it is actually much safer to have a bottom driven impeller which comes from the bottom and it sits only a few inches above the top. And these systems actually are much more stable in the sense that the stirrer shaft is much less likely to break if you have a very viscous culture. But otherwise, the default one, I mean, so all our the research lab has practically only top driven fermenters. So with that background, let me come back to second topic, which is impellers. Now, these impellers, they also come in many different uh, flavors, and I'm going to show you. This turns out to be important in this chapter because many of the questions sort of ask you what will happen with this impeller, what will happen with that impeller. So, uh, what is shown over here? Can you see this figure on the right hand side?
Yes, sir.
Uh-huh. So on top, right at the top, is what is listed shown as 6 flat blade disc turbine. This is basically you can think of the impeller as something that looks like this. Maybe I have a better picture, a photo. Um, right, this one here on the left side. Can you see that? This
Yes, sir.
it says Rushton turbine. This is the same thing as a six flat blade disc turbine. So there's a disc, right? On that disc, there are six flat blades. They're not flat because, as you will see later on, instead of making them flat, you can make them pitched, which is to say at an angle. But in this case, there are six blades, they are flat, and as you can see, they are mounted orthogonal to the disc. So as the impeller turns, these flat plates push against the liquid. And as we will see later on, they also seem to serve some function in causing excellent gas mixing. Now, because these blades are flat, as the impeller turns, you can see that the liquid is pushed in the radial direction. Okay, so these are called radial flow impellers. The Rushton turbine or the six flat plate disc turbine is an example of a radial flow impeller. And each type of impeller has a unique flow pattern. So we're now next going to discuss the liquid flow pattern that will occur when you use the Rushton or the six flat blade disc turbine. If you take a look at the figure on the top, you can see, I'm talking about the reactor where I've labeled the radial flow impeller. You can see that basically the arrows are showing you the flow of the liquid. And you can see that in the immediate vicinity of the impeller, the liquid is moving radially outward. Once this liquid hits the boundary of the reactor, part of it starts to move upward, goes all the way up, and then is recycled back to the impeller. And another part of the stream that hits the boundary of the reactor comes downward and then recycles back to the impeller. So it's sort of every time little pockets, little packets of liquid, they come to the impeller where they receive a lot of momentum and then they are pushed and then they do this macro circulation pattern where they go round and round. In contrast to these radial flow impellers, you get what is called an axial or a downward uh, downward. The picture down there shows you two impellers. One is called a propeller, which is just like the propeller in a ship or those old-fashioned propeller planes. And the other one is a pitched blade turbine, which is basically a Rushton turbine, but the blades, instead of being orthogonal, are now pitched. They are at an angle. And when you turn the pitched blade turbine, you can turn it in either direction. One of the directions will lead to the blade pushing the liquid downward. So that's why it's called an axial flow impeller. And in the picture that is shown, you are turning this impeller in such a way that the liquid is being pushed downward. In principle, you can also push the liquid upward by turning it in the opposite direction, but nobody uses it. For reasons that are not entirely clear to me, there must be some reasons for it. So the flow pattern that you get when you use the axial downward flow impeller, such as the propeller or the pitched blade turbine, is the picture shown over there. You have basically two streams coming down, basically stream coming down, which then bifurcates radially outward into one that goes to the left, the other that goes to the right, and then this entire thing goes upward, and then on both sides it turns back and comes back to the impeller. So these are the flow patterns, and the main point to be made here is that different impellers give you different flow patterns, and these flow patterns and impellers are used depending on the rheology of the system. So maybe I should also show you that. So I have just shown you so far only two of the impellers. On the left side is the Rushton or the 6 flat blade disc turbine. On the right side, I showed you two axial flow impellers, the propeller and the pitched blade turbine. But you also have additional impellers shown in the bottom panel, such as the anchor, the gate anchor, and the helical screws. These three impellers shown at the bottom are typically used in high viscosity media. So let me show you the picture here. Um, let's see if we can. Ah, okay. So the figure on top is showing you the ranges of the viscosities in which the various propellers are used. Right at the bottom, the viscosity 1 centipoise, and then it's a log scale. You have 10, 10 squared, 10 cubed, 10 to the power 4, so on and so forth. The viscosity is going up in multiples of 10. And on the y-axis, they're showing the impeller type. So you can see that basically the propeller and the Rushton turbine are used when the viscosities are low. When the viscosities become really high, you start using, you know, those other ones I showed to you, the gate anchor and the helical screws. So these three ones at the bottom, the gate anchor and the helical screw, these are used when your viscosities are on the order of 10 to the power 5. That means you have mixtures that are 5 orders of magnitude more viscous than those of water. Um, Another point regarding these various impellers is that you know there are two functions of an impeller. One is that they generate turbulence, and the other is that they generate flow. Flow meaning they push the liquid around. And basically, it turns out that impellers that do one thing well do a pretty poor job of the other one. There seems to be a trade-off between the two, and the reasons for me are not totally clear. But you can see that the gate impellers, for example, they generate very little turbulence, but they have very high pumping capacity. In contrast, the Rushton turbines at the bottom generate a lot of turbulence, but the pumping capacities are relatively low. So uh, that is essentially covering everything you need to know at this point in time about impellers, right? So basically, what did we just cover? That there is a drive at the top, but it can be at the bottom if you want to save on head space, head plate space, or your liquid is very viscous. But most of the time it is at the top, and then it passes on to a stirrer shaft and transmits the torque ultimately to the impeller, which agitates the liquid. And the impellers come in various categories. They can be either um, radial impellers, radial flow impellers, or they can be axial flow impellers, typically downward flow. And these impellers, different kinds are used depending on the type of liquid you have, whether you want to generate turbulence or whether you want, um, you know, pump the liquid at high levels, because these two seem to be mutually exclusive. And the last point I want to explain is these baffles. Now, it's very easy to see what this is about. I mean, if you um, so um, basically, if you did not have these baffles, then as shown in the picture on the right hand side, make it a little bit bigger. So the picture on top is showing you that if you have pure circular flow, right? I mean, if you didn't have these baffles, then basically you have what is called circular or vortex flow around the stirrer shaft. Uh, from the top view, which is shown as A on top, and B is the front view, you can see basically all you have is like a vortex which caves in at the stirrer. And this is not turbulent flow. The liquid is literally turning like a solid body. So the baffles are introduced basically to break this laminar flow into a turbulent flow. So they create turbulence. That is the job of the baffle. Now these baffles, they come in two varieties. You know, if you see the picture on the left carefully, you can see that there is a slight gap between the reactor vessel and the baffle. This is actually one special case, and more on that in the next figure. So this is showing you that the baffle, the relationship, the spatial relationship of the baffle to the tank wall. On top, you can see the baffle is literally attached to the tank wall, so there is no gap. You know, there's no clearance between the baffle and the tank wall. This is typically used when the viscosity of the liquid is very low, right? If the viscosity of the liquid becomes marginally high, if it is intermediate, you use the picture shown in B. So, you know, you place the baffle, but you put a little bit of a clearance out there because in very viscous liquids, the arrangement on top with no clearance at all is very, very difficult to move the liquid. And the the picture at the bottom, it's still further modification at still higher viscosities. You basically tilt the baffles. Apparently, that makes it still easier to move the liquid. So that is the general picture. I've actually captured about 10 pages of descriptions in in I think what 20 minutes by just going through all the pictures that are there. Now, before moving on, is that part clear? I mean, that's pretty straightforward, right? I'd actually asked you to read this
Yes, sir.
part. Now, some dimensions that it is good to know. These will be used a lot in the coming chapter. So, um, it's also good to have a feel for the order of magnitude of the dimensions. So, everything in this picture is going to be given in terms of the tank diameter. So, everything is sort of related to if the tank diameter is this much, then this dimension is so much. So the tank diameter is basically denoted dt. And you can see that the liquid height in most reactors, these are the reactors that we see, for example, in the lab, um, the liquid height is on the order of the tank diameter, maybe 1.5, something like that. In the industry, this can be 2 times, 3 times. The height can be made larger. This is called the aspect ratio. Um, then coming down, you have what is called the impeller, right? You can see the picture. And we have this very important dimension called the impeller diameter. So this is the diameter of the entire impeller, which is denoted d sub I. Um, make it bigger. So this d sub I is on the order of 1/3 of the tank diameter. Again, when I use the word order, I mean it can be 1/3, it can be 1/5, but approximately 1/3. Yeah, it can be, 1/4, 1/2, but this is the, you could call it the nominal value of the impeller diameter. And then another property of the impeller is its clearance, which is to say the distance between the impeller boundary and the impeller on the bottom. Another name you will see is they give it off bottom clearance. This should be called really because it's the clearance from the bottom, and this is on the order of dt over 4. So uh, this whole picture is a little bit asymmetric, right? Because if the height is on the order of dt, then the impeller is placed basically 25%. Uh, if the total height is ht, this is placed at about ht over 4. Ci is on the order of ht over 4. And finally, uh, there are some dimensions related to the sparger diameter, and the sparger separation is the distance of the sparger from the. It sits at the below the sparger sits below the impeller, and the distance is called as the sparger separation. So, roughly speaking, as we will find out, the air bubbles come out of the sparger, then they are sort of entrained, they are pulled in by these flat blades or pitched blades on the impeller, and then the air is kind of thrown along with the liquid, right? So, the reason why you put this sparger at the bottom is that the impeller is playing a very important role in breaking up the air into smaller bubbles and moving it through the reactor along with the macro currents, the macro circulation currents that I had shown to you earlier. So finally, um the baffle clearance, which is denoted CBF on the left, this is very small. As you can see, it is between 0 and 1/50th of the tank diameter. That too, only when the viscosity of the liquid is low. If the viscosity of the liquid is high, um, there is, it's not. So, first of all, the baffle clearance is there only when you deal with high viscosity liquids. If the viscosity is low, there is no baffle clearance at all. And finally, the baffle width, which is on the order of 1/10 of the tank diameter. These are just some numbers to remember. It would be easier if we had access to a functional reactor so that you could simply see. But those are the rough dimensions of the key components of a reactor. So, if that part is now clear, I can kind of move on to, um, I suppose, the gas flow patterns. Okay. Um, all done. Um, I should just point out there is something that I have not done in much detail, which I will point out. This is really, I mean, I've covered pretty much everything. But section 8.4.1 describes in great detail, you know, the flow patterns that are observed. This is with the Rushton turbine, yeah, and also it also describes in great detail. And by the way, these flow patterns are described without gassing, which is to say when there is no gas, and what happens when there is gas as well. These are actually kind of tough slogging. I mean, it's very detailed descriptions. I urge you to read it yourself. They have done this for both Rushton impellers and pitched blade impellers. But I want to go straight away to this figure. Um, this is showing you. So we are now already at the point where we are considering the first major problem, and that is how do you ensure that you have good mixing of the gas in a reactor, right? It comes out of the sparger, but you want the bubbles coming out of the sparger to first break into smaller bubbles and then get dispersed throughout the reactor. And what we're looking for is some quantitative way of assessing how should we do this in order to make sure that the gas is fully dispersed in the reactor. Actually, the more precise problem will become ultimately that we will come up with just how rapidly should we rotate, what is the RPM of the impeller to make sure that we get good gas mixing. So um, the intuitive picture is shown over here in figure 8.18. Okay. So imagine first of all, first I'm just giving you uh, um, the physical picture, and then we will make it. We'll get some mathematical equations to tell us exactly how to operate. So imagine first of all that you maintain a constant gas flow rate in a reactor. So you're pumping gas in through the sparger. Let's say the reactor has the volume, let's say 1 liter, and you're pumping gas in at a constant flow rate. So you're keeping the flow rate Fg constant, say at 1 liter per minute, right? And you are increasing, this is an experiment that you're performing, and you're increasing, progressively increasing the RPM. So let's say you start with a really, really low RPM. Let's say you start off over here with like 10 RPM. And your gas flow rate is, let's say, 1 liter per minute. Now, because the impellers are turning very, very slowly, their ability to entrain the gas and disperse it is very poor. Because of which, the gas basically flows straight upward, vertically from the sparger without getting dispersed at all. And this is an undesirable situation that is called impeller flooding. So, on the left hand side, what you're seeing is what is called impeller flooding. This is what happens if the gas flow rate is relatively high compared to the impeller speed, right? So your impeller speed is kind of low, so low that the gas does not get entrained, does not get trapped into the recirculation patterns created by the impeller, and basically flows straight upwards in a pathological situation called impeller flooding. If you increase now the impeller speed from 10 RPM to say 100 RPM, so if you increase the impeller speed, keeping the gas flow rate constant, so we're still maintaining the gas flow rate at 1 liter per minute, and we increase the the RPM from 10 RPM to 100 RPM, what you find is the picture shown in the second case, where the gas now starts to spread. But notice that below the impeller, there is no gas dispersion. All the dispersion is taking place above the impeller. Okay, so the situation is better than impeller flooding, but it's still not quite ideal. This picture is called impeller loading. So impeller loading is when um, this is impeller loading. Impeller loading is when basically you're getting good circulation above the impeller, but no circulation below the impeller. And if you increase it to a still higher level, say 600 RPM, then you get the picture on the right where you get massive recirculation of the gas both above and below. And this picture, this desirable picture, is what is called complete gas dispersion. So this is the third one. And this is where you want to be. Now, while explaining this, the mental image I gave to you was that the gas flow rate was constant and I was increasing the impeller speed. But you can just go do the experiment in the reverse way by keeping the impeller speed constant and increasing the gas flow rate, right? And if you do that, then you know you move in the backward direction. So basically, at very very low flow rates, right, and constant and sub I, you will get a picture on the right. As you increase the flow rate, you start moving leftward. And when the flow rate becomes very, very high compared to the constant impeller speed at which you're operating, you get the picture on the left, which is impeller flooding. So, roughly speaking, you can see that the gas flow rate and the impeller speed, they have opposite effects. Is that part clear? This is all intuitive. Now I'll kind of move to the mathematical part. Any questions so far about? Uh, so I should just mention that um, the uh, reason as to why you get these patterns is covered kind of nicely in this part here, which is kind of long, but you can get a better sense of it. For us, it's enough to know that this happens and move straight away to the mathematics. So, any further questions about what I have just mentioned? None? Okay. Then let's move to a mathematical derivation. So, um, is okay. So, the topic that we are covering is the first of the three topics that we will cover. This is on mixing. And what we want to cover is how to make sure that gas is well mixed. Okay, so um, now um, the uh, the basic ideas that we use here will be what are called scaling arguments. So let me first of all uh, introduce some numbers. So the first important thing here is we need an estimate of the pumping capacity of the impeller pumping capacity. And well, um, the key number here is a number which is called the liquid flow number. There is a number called FL, which is called the liquid flow number, which is defined as the actual flow rate leaving the impeller divided by the ideal flow rate leaving impeller. So, I mean, you can imagine that the impeller is kind of pushing the liquid, and uh, people have found this ideal flow rate or ideal, they call it pumping capacity of the impeller, right? This quantity here. This is estimated by N sub I. So this is basically estimated by the velocity impeller. This is impeller tip velocity multiplied by area, some measure of the area. Now, the impeller tip velocity is nothing but, this particular quantity is nothing but the RPM multiplied by the impeller diameter. I mean, this is that omega R formula that you must have seen. So basically, this is essentially the RPM is denoted by N sub I. This has units of revolutions per minute or revolutions per second. And the impeller diameter, this is DI, this is impeller diameter. The product of these two is giving you the impeller tip velocity. And this has to be multiplied by some measure of the area, which is taken to be DI squared. So a measure of the ideal flow rate leaving the impeller, keep in mind, these are order of magnitude calculations. These are not exact numbers, is basically, so this is actually called V sub I. V sub I is velocity of the impeller tip. V sub I is equal to RPM of the impeller, or number of RPMs executed per unit time, multiplied by the impeller diameter, which is DI, and then the area is DI squared, so the whole thing gives you DI N sub I DI cube. And people have found, so this is denoted, we can say this is Q. So we can say that basically, according to our notation, we can rewrite this as simply FL is defined as the actual flow rate Q divided by N sub I D sub I cube. And many experiments have shown that basically this number FL is on the order of 0.8 for various kinds of impellers. So that implies that basically Q is equal to FL multiplied by N sub I D sub I cube, where FL is on the order of zero point 0.8. Another way of saying this, which will be more important for us, is simply that the rate at which it pumps scales as Ni Di cube. For us, the exact number will not be that important. We are only interested in the ratios. So the main point here is pumping impeller pumping capacity is proportional to N sub I Di cube, which, as you remember, came out of the formula Ni Di multiplied by Di squared. That's how we got it. Is that part clear? That the pumping capacity
Yes,
of an
sir.
impeller is basically N sub I D sub I cube. Okay. Now, the second point, more important, getting to how do we decide? So, actually, what we are getting to is this is predicting the gas flow pattern. In other words, we want some quantitative criteria to be able to decide whether we will get impeller flooding, which is the pathological case where all the gas is sort of flooded around the impeller. Do we get impeller loading, which is when gas is recirculating above the impeller, or do we have complete recirculation, complete circulation, or complete gas dispersion, which is the case when the gas is recirculating all over the reactor? How can we decide what do we have? Well, it turns out that this whole thing can be predicted if we know two numbers. So the gas flow pattern can be completely predicted. Completely predicted. Um, for actually, I should for Rushton and also some other impellers, some other impellers. If we know there are a few things we need to know. The first thing we need to know is this is called the gas flow number. Or some people call it the aeration number. This is the previous one we defined was called the liquid flow number. To distinguish it from the liquid flow number, we will call this FL sub G. So this is the gas flow number. And the gas flow number is defined as the gas flow rate in liters per minute. divided by, so keep in mind, these are all dimensionless numbers. Provided you use the same units, that is, yeah. So if this is in liters per minute, and this one is also in liters per minute, you get a dimensionless number. And the gas flow rate is denoted by the symbol F sub G, and the impeller pumping capacity we just found was proportional to N sub I D sub I cube. So this is what defines our, again, we don't worry about constants, right? We had the actual impeller pumping capacity was, you know, FLG times NI DI cube, but we don't really care about constants. We only worry about variables. So this is called the gas flow number, which is the ratio of the gas flow rate to the liquid flow rate due to pumping by the impeller. And the second thing you need to know is what is called the Froude number. This you should have seen in the transport phenomena course. This is one of the many numbers that appears. This number, which is called the Froude number, is defined as inertial force by buoyant or gravitational force. So I should mention this here. I mean, one of the numbers you certainly remember is the Reynolds number. The Reynolds number, if you recall, is the ratio of the inertial force to the viscous force. So, what are we talking about here? Well, what we're talking about here is that momentum can be transferred by various mechanisms. You know, momentum can be transferred by convection, which is to say bulk flow, where packets of liquid just jump around in big chunks, carrying momentum with them. This is called convective momentum transfer or inertial momentum transfer. And when this momentum transfer takes place in this fashion, it generates what are called inertial stresses or inertial forces. So these involve bulk motion. Then we have another way in which momentum is transferred is of course by diffusion, right? And that's what is called uh, viscous transport of momentum. So when you the mu times dvx dv by dx or whatever it is, um, that is describing momentum transfer by diffusion. In addition to momentum transfer by convection and by diffusion, you have external forces that can act. For example, you can have gravity, you can have pressure, and you can have even other forces which are not typically considered in a transport phenomena course, but if you're an electrochemist, there can be electrical forces. But in your transport phenomena course, certainly gravitation or buoyancy was always there. So the Froude number is sort of taking the ratio between the inertial force and the buoyant force, or the gravity, the term with rho g in it. Just like the Reynolds number takes the inertial force on top and the viscous force at the bottom, this is taking the inertial force on top and the external force called buoyancy or gravitation at the bottom. Now, how do you calculate it? This is a good thing to remember. Uh, Whenever you have an inertial force, it is due to inertial stresses. Now, the inertial stress always has order of magnitude of rho multiplied by the velocity squared. So, in this case, the most obvious velocity to use is again the impeller tip. This is a measure of the stress created by convective momentum transport, and that must be multiplied by area to get force. So it is multiplied by di squared. In contrast, the buoyancy for the stress created by gravity is essentially rho times g times d sub I. This is, if you remember the formula rho g h as the pressure at a particular point. I mean, pressure has units of stress. So you can think of this as the force per unit area created by gravity. And of course, this also must be multiplied by some measure of the area, which I have taken to be di squared. But this cancels out, and ultimately you end up with vi squared divided by g times di. Okay? And since vi equals n sub I di, then this is basically n sub I squared divided by, this is n sub I di divided by g, since v sub I, which is the velocity of the impeller, is n sub I times d sub I. So these are the two numbers. There is a third number that is important, and the third number is the ratio of impeller to tank diameter. So this is basically di, the impeller diameter, divided by the tank diameter, which I told you is typically on the order of 1/3. Okay, so this is, I mean, there is no need to add anything to it. So how do you now classify the behavior? Well, here is the formula. This is the typical type of formula you get. This is for a Rushton impeller. Let's just see. And you would have similar formulas for other impellers. So for a Rushton impeller, the transition, this is I, the transition. So this is the transition from impeller loading, so between impeller loading and complete gas dispersion. Complete gas dispersion. So is given by the formula. So this occurs precisely when FL is equal to this quantity. This is actually better understood. Um, So these are formulas. Um, I should correct this. Actually, maybe this is not right. Better to write it this way. It will become clear as we proceed what I'm doing. So, um, graphically, this implies that log, right, to the base 10 of FL under bar of G equals, this is log of DI, this is 0.2 DI over dt to the power 0.5 plus zero point 0.3 log of FR, the fruit number. Okay, actually, what I am trying to show you, maybe I should make a diagram here. This has the fruit number over here and the gas flow number over here. We are assuming that di over dt is fixed. So there are three parameters: the gas flow number FLG, the fruit number FR, and the ratio di over dt, which we are holding fixed. And what this basically formula is showing, take a look at that formula. This is actually plotted on log to the base 10, and this is log to the base 10. And if you do that, you do this thing for fixed di, this is an impeller of a fixed ratio relative to the tank size, then basically you can see this is a straight line of slope 0.3, right? So this is basically a line. This is the line uh, FL underscore G. And what they are telling you is that this line defines the boundary between complete mixing over here and over here you have impeller loading. So going back to uh, this page, uh, B is impeller loading and C is complete gas dispersion. The transition from the middle case to the right case or the right case to the left case is defined by this line whose equation I have just written, which is right here. Okay, so this is giving you, so let me read. The transition between impeller loading and complete gas dispersion, correct myself to be consistent, uh, this is complete gas dispersion is given by this line. This line has the formula which is shown over there, right? Log of 0.2, so it will have an intercept. This intercept is log to the base 10 of 0.2 di over dt to the power 0.5, and it has a slope of 0.3. Now the next thing gives us the equation for the transition between impeller flooding and impeller loading. So far we have the transition between impeller loading and complete gas dispersion. The next equation will tell us the equation. So the next one says the transition between um, impeller flooding and impeller loading is given by the equation, which will again correspond to a line. It's basically FL of G equals FL, I put over bar for upper boundary, and that is equal to 30 times di over dt to the power 3.5 multiplied by the Froude number, which implies in the log scale. I will not put the base 10, just assume that that is the case. This is FL over bar of G equals log of 30 times di over dt to the power 3.5 plus log of Froude number. So now this gives you the second line, which probably goes something like this. You can see it's a straight line again, but now it has a slope. The slope is obviously 1. So this line has a bigger slope. This is all being done for a Rushton impeller. This is slope 1. And over here now you have impeller flooding. Okay. So may I ask now, is that so far so good? This is the picture that we have drawn. So um, and this will have, you know, a will have an intercept of, just do the calculation. Its intercept, its y-intercept will be log of 30 di over dt to the power 3.5. So this intercept over here can also be written down. Now the important point here is, how does this relate to what I just explained? I just explained, for example, that if you keep, um, uh, you know, the flow rate of the gas fixed, right? If you keep the flow rate of the gas fixed, if we repeat, let me go back and show this to you. Um, if I told you that if you keep the flow rate of the gas fixed and increase n sub I, you move from impeller flooding to complete gas dispersion. Correct? And conversely, if you hold n sub I constant and increase G, then you move in the inverse direction. Well, how does that show up on this figure? Um, just to see if you people are still. Can you see how the first case would be true? If you increase the gas flow rate, I should write down the formulas too. The Froude number is n sub I squared d sub I over G. This is F sub G divided by n sub I d sub I squared. So if I increase the gas flow rate at fixed n sub I, I increase the gas flow rate at fixed n sub I, what do you think is happening? Is anybody awake? Is anybody there?
You would increase if you increase the gas flow rate at fixed times.
Is anybody following? What happens when I increase?
Yes, so we move towards impeller flooding from complete gas dispersion to impeller flooding.
Right? Can you see why? I mean, basically, you are increasing f sub g at constant n sub I. That means this number FLG is increasing, but your Froude number is constant, right? So the Froude number, so this is the path. Okay, if you increase f sub g at constant n sub I, because if n sub I is constant, then the Froude number is constant. Keep in mind, di is fixed. Di and dt are fixed. So if di is constant and n sub I is constant, then the Froude number is constant. And increasing f sub g merely increases the gas flow number while the Froude number is constant, so you're moving vertically upward. And therefore you pass from complete gas dispersal. This is the going backward case. Now let's take the other case, which is increasing n sub I at constant d. Which way will you move?
Rightward along the x-axis.
Rightward. Yeah, so basically you will have a motion that kind of goes like this. Because f sub g is, so this is the motion. If increase n sub I at constant f sub g. Now you can see that if f sub g is constant and you start increasing n sub I, then FLG is coming down and the Froude number is going up. So that means the y coordinate is decreasing. So this is sort of like a hyperbolic change, and that's what's happening here. So when you increase n sub I at constant g, at constant f sub g, you move from impeller flooding to complete gas dispersion. So you can compare that with pictures that I just showed. So increasing n sub I at constant f sub g, that is this picture here, you're moving from left to right. Constant n sub I, increasing f sub g, moving to the left. So this is actually kind of important in the numerical problem. So let's take a look at one of those. You can now see how you can attack a problem. I'll just describe the problem to you, and then you can take a look at it on your own. So here is a practical use of this formula. They are basically taking a fermenter, giving you a fermenter of diameter and liquid height 1.4. Basically, they have given you, this is saying that dt is equal to ht is equal to 1.4. These dimensions are given, and they're also telling you that it is a Rushton impeller, and they're telling you the diameter of the impeller is d sub I is 0.5 meters given to you. And they have also given you the off bottom clearance, which is what is called C sub I, and they have told you that it is operating at n sub I equal to 75 RPM. And basically the fermentation now, so they've given you the specifications of the impeller. Now they're saying that the fermentation broth is sparged with air at a volumetric flow rate of 0.28 cubic meters per minute. Now here is the key. Halfway through the culture, some of the bearings in the drive fail, and therefore the stirrer speed is reduced to 45 RPM for the remainder of the process. And the question is, first of all, under the normal operating conditions, that is to say, before the bearings broke down and the stirrer drive failed, it was operating at 75 RPM. So at 75 RPM, is the gas completely dispersed? And the second question then says that after the stirrer speed is reduced due to the abnormal operating conditions, right? It has gone from 75 RPM to 45 RPM. What is the condition of the impeller? Is it flooded, loaded, or for that matter, remains completely dispersed? You need to check. So this is essentially saying, giving you the conditions, asking you to find what is the condition. Is it loaded, flooded, or completely dispersed? Is the question clear?
Yes, sir.
Okay. So now the way to tackle it, I think that I'll probably, maybe, I don't know. I think the way they do it is kind of, so the way I have done it is not the way, the book doesn't organize it this way. But we can, so this is example 8.1. Actually, I think we've run out of time, so we'll stop at this point. You can take a look at, try to do it. Basically, in every single case, you have to find out what is the value of, ideally, you just go to this diagram, find out the value of FLG, find out the value of FR, and see where you stand. That's all there is to it, right? These two parameters are given to you, and that's all you need to know. Is that part clear? You can try it out on your own, and we'll pick up on it next time. Okay, all right. So I'll see you on Thursday. I hope you're making progress on the homeworks. Then now, maybe, are you having a lot of problems, or is it working on pretty well?
We're able to solve, I have a few problems today. So maybe if I have a doubt in them, I'll ask in the back class.
Okay, all right, then we can keep going at it. So we'll pick up on Thursday. I think wrap up this section on Thursday. Okay.
Thank you, sir.
Thank you, sir.